Okay. Hello, everyone. Yeah, energy. Thanks, everyone, for coming, especially to being the last day. And most of the people that we knew are going home. So we are very glad for us to have you here. Thanks the La Villa Hacker people that are here, I'm sure, because I cried for that. Yeah. And, well, we are prepared now to talk to you about railroad hacking. We call this. It's working? Not working? Okay. We are Gabriela Garcia and David Melendez. I am a security software developer that got into hacking and hardware hacking because of the hardware hacker people that they like to introduce you to the weird world. And David Melendez, I am the embedded software engineer that is here to talk to you with me about railroad hacking. We call this the dark territory because in railway sector, a dark territory is a section of the railway that lacks remotely control of signals and you have no automatic blocking systems. So in this area, the communication and coordination is really exclusive on the railway operator, and the term has gained popularity in railway hackers to describe sectors that lack supervision in any other kind of way. So, we are introducing you Fun with Trains. As you can see, graphic design is our passion. So let me introduce you to some concepts. For example, the railway block. A railway block is a section that is normally no more than one train can be present to evade collision between two trains. This block session can be between stations and can be between signals for the railroad control people to be able to control the passes of the trains between these blocks. To know where and how they have been passing the trains, we have axle counters that are systems that count the axis of every train, and every train needs to be the same amount of axles in the first one and in the last one. It's nice because you don't lose people or half of your train, so it's very cool. And we can have train blockings in different ways. For example, we can give a token. It's vintage, but it's still happening in some parts of the world. You can give the railway operator token, and he takes it. It's vintage, okay? It takes it, and then you know that this train has passed through your station. The next technological advancement has been to call people instead of giving them a token because it's weird. So the telephone block is just to tell the next block that the train is passing through your block. It's less vintage, but vintage too. And then we pass it to the train blocking, the electronic train blocking. What we have is slices of railway that are controlled by signals or controlled by a central control operation center that blocks the slice of railway when the train is passing out, taking into account the data received through the axis counter. We have it in one track, we have two tracks, and we have reversible two tracks. So we can have control in every direction you have your train passing. The control is just set by the side where these beacons in the railway are set. So if you are in one direction, the beacon that is controlling you is in the right side of the railway. And if you are in the opposite direction, in your direction there will be another beacon controlling that you are passing through this segment. And this is the centralized traffic control. This is especially in Madrid called Chamartín. And there are like lots of people working here controlling that the trains don't collide, especially. We have based this investigation in one of the systems that is present in Spain that is called ASFA. In Spanish is Anuncio de Señales y Frenado Automático. In English, Announcement of Signal and Automatic Braking. What it does is support the train circulation based on a coil capacitor circuit connected to a signal, and depending the signal, the aspect they need to transmit one frequency or another in the onboard equipment. So this is the whole process. You have a railway signal that connects to a unit that gives a signal to a beacon. The beacon is received by the perturbation, is the name? The perturbation is received by the antenna, and this antenna gives a signal to a console that is inside the train and gives different aspects related to different signs. The first of all is that you can have fixed aspects that are signals or beacons that only transmit one signal, and variable aspects that have beacons that have different signals. And it depends on the frequency they leave the antenna is the aspect that the railway operator is receiving inside. So the first problem is that, as you can see, a couple of different signals give different aspects, or the same range of frequencies give different signals to the railway operator. So, for example, the L1 and the L3 are in the same range of frequencies, so we can have little problems when we are not controlling it as much as we need. And this is the panel that the operator receives here. It's completely in Spanish because this picture is taken on open source documentation that the railway company in Spain have completely publicly available on the internet. So this is a screenshot of their documentation. And this is what the train driver sees. As you can see, this little blue dashboard has some buttons that represents the acknowledgement of the train driver that they have received this signal or the advice of these signals. So they push, I have acknowledged this signal, and I have to keep moving forward. And we get into what we call the dark territory, because there has been several serious accidents in Spain related to the control of the signals. The first one is the Huarte Araquil. It was like 30 years ago, and it was related to not having any kind of beacons or signals or systems of control on the railway. And the train driver saw a signal, but misconfused the signal and misinterpreted what he saw, and lots of people died. And then, like 10 years ago, when was the Galician accident? Was 10 years ago, right? They had a huge accident in Spain too, where kind of lots of people died because there was a misconfiguration between other factors. There was a misconfiguration in the ASFA system, so it could be not completely avoidable, but less difficult to fix. So we have these beacons. These are the beacons that we have in the ASFA systems, and these beacons are sit on the railway, and you can receive it by the capture. So, go ahead.
So I have to work here. So we have the beacon in that the black box. The wood doesn't count. It's only the black box, and inside this black box is a coil and a capacitor. So we have a coil capacitor circuit in closed loop, no batteries, no voltage here, no batteries, no IC power. So it's a passive device that is powered by the train when the train passes along the track. So we have here a very simple circuit with a coil and capacitors in parallel. So I'm going to explain why this setup makes sense. So the technology behind the ASFA system is based on induction, as you can find in your kitchen or in your phone charger, wireless, of course, and even in RFID tags and so on. But it's a very primitive kind of RFID tag. Very primitive because there is no data transmit, but it's only an aspect transmit. So we're going to see that.
All of this is in Spanish because it is open source.
Yeah. All of this is publicly available if you Google that. So a guy put this on internet that, I have to repair an ASFA tester. An ASFA tester is a device that it will be on the train part. So this device, you put this device above the beacon, and this device read what kind of beacon is. So we have two coils here. The two rounds, the two circles are two coils. One coil is for transmit to give power to the beacon, and the other one is to receive power. So if you what about if you use a circuit with a coil and capacitor to emulate a beacon? We could replicate a beacon, and we could make a fake beacon. So we require wire and a capacitor. That's all. It's enough for that. So I think this is the most important slide here in this talk, because it represents very well how the setup is configured. So we have the beacon itself in the track, and the beacon is, as you can see in the diagram, we have a coil and a capacitor. We represented a variable capacitor because you can configure it, you can change the capacitance of the circuit to change the aspect. For example, if I want to transmit a red light, we change the capacitance. This beacon is by default in red signal. Is the safest symbol that is red light, obviously. So if we put a small current temporarily to that symbol, we can change the aspect. So we only need power only to change from red to another symbol, for example, green or yellow. And the other setup here is in the train part. So we have a capture that it has two items. We have a 111 kilohertz generator, AC power. So we can generate a frequency of that kind with also a coil and a capacitor. And at the same time, the train has put together another device that receives that power by inductance coupling that, oh, I seen 111 kilohertz. That's okay. It's working. Okay? But when the train passes,
True. When the train.
When the train passes through,
when the train passes through the beacon, an inductive coupling is produced between the first coil that it transmits at 111 kilohertz, the second coil that receives that signal, and the third coil that is on the tracks that modify the inductance coupling to another frequency, to the frequency that is configured that beacon. It's easy to understand, yes?
Of course.
Okay?
Yeah.
It's okay.
Easy.
So, that's our desk. And we have the transmitter part. Firstly, to make the fake beacon, we need the framework, like Java, JavaScript, and so on. So Visual Studio Code. So this is our code editor. So we need a framework to test the beacon at that point that was not existing. So firstly, we need a transmitter. So we set up a coil and a capacitor that is suitable to transmit power at 111 kilohertz. Okay? We use an AliExpress device called NanoVNA that is a vector network analyzer that you can buy. It's cheap. So you can see the impedance, the inductance, the resonance, and so on. So this is the receiver part. Is more or less the same setup, but with instead of transmitting power, it receives power. So it's fine-tuned to capture frequencies from 50 kilohertz to 111. So it's very wide range to capture all the aspects of any beacon. So we have a signal generator, also from AliExpress, and
This is sponsor us.
yeah, and we receive that signal on the receiver part. So we already have the tester. So we need to make the beacon itself.
so what if two people here or not here could replicate this beacon and show it to you right now? Show it? So I pay you for that.
Aquí me toca a mí. ¿El tester?
¿Ah?
¿El tester o la?
No, la valí.
Ah, perdón, el tester.
Well, the most important part of this tester we did is a can of Morteruelo de Cuenca, which is, yeah. They are laughing because Morteruelo de Cuenca means meat in a can, okay? So it's what helped us to have like this coil or setup, and it works perfectly. So meat in a can may be a key factor in this tester, okay? And the second part is the beacon. Okay, so we could replicate the beacon by following the calculus that you can do with data that is completely, I repeat, completely available on the internet in open source information. So this one is the L5 as you saw. 1 second. Here, this one is the L5, the yellow sign. And for legal reasons, we cannot show you here on this stage the proof that this works, but outside of the stage, anyone that comes and asks will have the answer, okay? We don't want to go to jail, but we like to brag about our things. Yeah, okay. Todavía te queda explicar esto.
Hacking. So, as a computer engineer, I have to make the work of the electronic engineer here. So, if any electronic engineer here can come to explain that, and we rest here.
So, if there is any electronic engineer in the house, is there any electronic engineer here? Just raise your hand. Okay, we are sorry in advance.
So when you put current in a inductor and capacitive circuit, it's like a magic, you know. It's magic. Indeed, it's black magic here, because when you put a set of frequencies, so the circuit behave differently accordingly to the frequency that you put in that circuit. The computing engineers here, we couldn't understand this like the circuit has behaves as a capacitive, as a virtual capacitor, as a virtual resistance, or as a virtual inductor. It's okay, eh? That's cool. You don't get rid of virtual devices even if you are an electronic engineer. So the point here is to design a circuit that resonates at a very specific and very narrow set of frequencies. Indeed, you need to resonate very narrow interval of frequencies. So, as you see, as Gabs explained to you, we need a circuit that resonates at a certain set of frequencies to make the train think that this is a symbol. This is a real symbol, a red light, a green light, a yellow, even a yellow and green light that exists. It's Trainiac stuff, don't worry. So, we need that, but how do you do that? We are computer engineers. So we need to wire by public photos and seeing the device in real world. We can get the dimensions of the beacon. We can guess that because there is a public documentation, but they don't give you the exact details to make the beacon, obviously. So you have to guess that at some point. So guessing the dimensions of the beacon and the shape, indeed, we started to wire 1 turn, 2 turns, 3 turns, all day long. So we ask ourselves that, what I'm doing with my life? I could be in the swimming pool. So we end with a lot of turns, and what happens now? So we test it with the Nano VNA, and nothing works. The resonance of the circuit is very far from the target resonance. So we cut the wire and we put on the Nano VNA. So we start to wire another round of turns, and we saw real time how this graph moves in real time, getting closer and closer and closer to the target frequency of or the desired symbol. So turning and turning and messing it up, and what the fuck. So we achieve one symbol. So indeed, this is not a real coil capacitor setup, but it's a double inductor setup. There are two inductors put it together and taking advantage of the parasitic capacitance. We have a virtual LC circuit that makes the same work at the real device. We know that the real device is one coil and one capacitor, but this stuff is two coils put it together and taking advantage of the parasitic capacitance. So this is the center frequency, and less frequency, the circuit behaves as a capacitor. The more frequency is the circuit behaving as induction. So at the very exact point, the circuit is a resistance. So this is the graph that you have to see to make sure you are doing right.
In order to achieve.
In order to achieve the correct resonant frequency. The yellow line is the resonance that it has to be just in the middle of the graph. The green line is the impedance. So it has to be as low as possible at the resonant point. And the other one is the standing wave ratio. That is how well is the energy transferred from the system to outside and backwards. So that is the device. It's very, as you can see, it's very complex, very expensive. No.
And beautiful.
And beautiful, because it has, I think this Amazon cardboard.
Thank you, Amazon.
Thank you, Amazon.
I know that's beautiful.
What you have to use isolated copper wire. So if you can, once we have this item, we have to put glue on the device. That is very important because you make with the fingers any movement and the frequency changes. It's crazy. It's crazy. You take the device and no more works. No. So you have to glue of the wire to make sure that the center frequency remains at the target frequency.
In the tester, the most important was the can and here the glue.
The most important thing in the tester is the can of mortadelo of meat, and here is the glue, the key component.
Yeah, I'm sorry.
I'm seeing the electronical engineering looking at us. Sorry, really. I have stickers for you to compensate this.
So how do you know that this works? Well, firstly, you have to know what to see. It's a key factor. You have to know that I have to see things. So, in the picture of the left, we have the default frequency being received by the receiver device. So we transmit 111 kilohertz, and okay, I'm working. I'm receiving the same frequency as the train transmits. That's a permanent testing that the system works. So the left one, the right one is when you pass through a beacon. So you see another spike on the spectrum analyzer. You have another spike that represents the resonant frequency of the device, of the beacon. So that works.
Thank you for your sincere,
Thank you with this
sincere applause.
sincere applause. So, where should I place my fake beacon? Well, the official documentation already tells you where to put your device, your fake device. So that's the dimension. You have to keep a distance from the rails and a certain height from the slipper. So from the slippers, traviesas, slippers. So the most important thing that it matches the position perfectly to make all the setup take place, the induction coupling. This is not an radio frequency stuff, but it's more inductive coupling. We firstly thought that it was a radio frequency problem, but it's more like an inductive coupling, as Gabriela says to you. So, what about another systems all over Europe and worldwide? Well, in UK you have the AWS system.
Not powered by Amazon.
Not powered by Amazon. This is indeed the Spanish system is the most sophisticated legacy system, because they have more symbols to transmit. The UK system only has 2 symbols: go and stop. That's all. So you see a star in the cabin,
It's called the sunflower.
sunflower, and it's okay, not okay. That's all. And this is the industry. In German is very
What?
impronunciable.
Yeah. It's,
It has a name in German that we don't know how to spell. Okay, so let's call it Indusi and let's have some fun.
We don't have to offend German people. So there is also that kind of systems that it's based on the same principle. So, but they are not one-to-one compatible. So you will have to make your own device adjusted to that kind of setups. And that is the North American system that also is based on the same principle, but they are not entirely widespread on all the tracks. It's intermittent. It's an intermittent system. But it's based, again, in the same principle by induction. What about new things? Well, that's, we talk about a legacy system that was invented on the middle of the 20th century. So what about new system? We're talking about new because it was invented in the 90s. Okay, cool. Well, we have the ATCS, the European Trade Control System, that is based again on beacons, but they transmit digital data. So we will talk about this next year, maybe. So the main thing here is that all the European region has a very different systems, and they thought, what about a new protocol? So we have a new protocol that covers all Europe, but it is not implemented already widespread. Only in high-speed trains and very crowded lines, because it takes money, you know. So it combines beacons called Eurobalis. I like more beacons. And they combine that system with some kind of mobile communications, changing the protocol. It's called JCM Air. Air means railroad.
okay, wait. So, okay.
So as you have seen in the whole presentation, what we have discovered is that by inductive coupling, we can reach the most of the signaling system in Spain, sorry, because they don't use this system, ETCS, in the most of the railway segments. So what we have is now security problems that was in their time a really robust protocol, because these kinds of protocols are not being properly revised. So one of the main things that we receive when we talk about this investigation is why we are talking about this. And the reason is that we want to revise, or we want companies to revise this kind of systems. For example, we can adopt this new ETCS system. This system started being quite less robust, but now is like in level 3, developing level 3, and having very good results in terms of security. But it costs money, and money is a key factor in the decision making of the politicians and authorities related to this. So one of the other measures that we can offer, and we are completely willing to work with authorities in that, is the usage, for example, of trained drones that are being developed. This one is AI generated, okay? Because I didn't find the picture. Italy have now quite bigger but yet tiny trained drones, and these trained drones can be deployed through the whole railway segments to investigate or inspect the beacons, just to know if there is any weird objects, for example, in the railway, or anyone has covered these beacons. Because these kind of beacons, ASFA beacons, can be just shut down by putting above them a plate, a slice of plomo? Lead. Okay, so we are trying to make quite a concern and talk with our authorities to make them inspect them. Another object they can use are normal drones, just surveillance and looking at these railway segments, just to again know if there is any strange objects in the railway segments. And of course, we can use testers and pass testers more frequently, just to know everything is okay with the beacons. Actually, we don't have to create this chaos or fear, just want to have more intensity in the inspection rounds to change these devices into more newer devices around the world, because this investigation is based on the most robust legacy system, that is the ASFA, but here Amtrak is using it, UK is using it, not the same but less robust systems, and of course Germany, Austria, Hungary. So we can work to change this, or at least to revise this, to keep everyone safe around the world. So thanks everyone that helped us to get here. And of course, we are here for the questions. Yes? Yes?
That's fine.
Right. Thanks for the talk. Very educational, funny, and scary, honestly. When you have a signal that can display multiple aspects, how does that relate to the meat cans that are set on the track? Does it change its own resonance to reflect the current aspect on the signal?
Yeah, actually they do. because what differentiates one signal through the other is the state they leave the capacitor circuit in the train. So in the difference between these frequencies is the aspect the operator receives inside the train. Okay.
Okay, what are the related risks or threats related with this finding that you get? Mostly beyond that, to prevent accidentality in the trains. What are the risks?
The risks. Well, actually, we started this investigation because in Spain we are in alert, terrorist alert 4 from 5. So it's quite important because the biggest accidents that have happened in Spain had happened with trains. Actually, we have a real difficult incident that happened in the 11th of March that marked before and after on the way of that people sees the railway and the metro in Spain. So any people with the right amount of motivation and knowledge could exploit this. So we want to make a wake-up call before something like this happens and make people to invest more time and money into keep the safety around Spain and of course around the world, because this can happen like mostly everywhere.
So thanks. This is really fascinating. I'm curious to know if there are any other systems that the drivers rely on to make their decisions about how to, what speed to control the trains. Is it primarily these beacons that they're using for that? Or is there any other input they're also using to make the judgment?
Sorry, I didn't hear you
Not
anything.
sure.
Sorry.
Is there another system?
Well, the train driver has the real signals, and the system is an acknowledged system to make sure that the train driver has seen the right signal. So by default, there is no other resource, and the point here is that you could make a red signal device in the middle of the track with no lights, for example.
Yeah. Okay. Thank you.
Any other questions? More questions?
More questions?
No?
Thank you.
Thank you very much.